Hello, my name is Jolene Rhodes, and this lesson is going to focus on applications involving exponential functions. What we're going to do is take several application problems and write the corresponding exponential function that represents that application. Okay, let's take example 1. There are two people who decide to start a rumor. The rumor spreads so that the number of people who have heard it triples every hour. What we want to do is write an equation for the number of people who have heard the rumor at any point in time t. Now, I think the easiest way to start sometimes when you're writing an exponential function for an application is to make a table. So let's make a table over here of the number of people that have heard the rumor at particular times. I'm going to use t for time and p for the number of people that have heard this rumor. Now we know at time 0 there are just the two people that have heard that rumor, and they're the ones that basically are going to start that rumor. Now after 1 hour, what do we know? We know that there are 3 times as many people that know that rumor. So in other words, there's 2 times 3 or 6 people. So 2 times 3 people that have heard that rumor. The next hour, this number triples again. So what we're going to do is take our 2 times 3 one more time, because we're tripling yet again, and we're going to have 18 people that know that rumor. At time 3 hours, this number is going to triple again. So we're going to take our previous number and again multiply by 3. 18 times 3 is 54. So 54 people now know our rumor, and so on and so forth. Now when we look at the pattern that's in this table, at 1 hour, this is 2 times 3 to the first power. At 2 hours, this is 2 times 3 to the second power. And at 3 hours, this is 2 times 3 to the third power. What I want you to notice is that the number that's changing in each of these cases is the exponent, and this is why we end up with an exponential function. So if I were to write an equation for the number of people that have heard this rumor, the number of people is going to be 2, and that 2 came from the 2 people who originally started the rumor. That's how many people knew it at time 0, so our initial amount of 2. Then what we're going to do is we're multiplying by 3 because the rumor triples the number of people every hour, and it is every hour. So up here is how many hours, in our exponent, is how many hours have passed by. So we'll have a final equation of p equal to 2 times 3 to the t power. Now this will give us a way to find the number of people that have heard this rumor at any point in time. So if we were interested in finding the number of people that knew this rumor after 24 hours, what we could do is simply plug in, so how many people knew this rumor after 24 hours, what we would be doing is finding p, and t is 24 hours. So let's see how many people know this rumor after 24 hours, which I think is quite a few. Using my calculator, that gives me the number of people of 5, 6, 4, 8, 9, which is a very, very large number of people to have heard this rumor. Okay, let's move on to example 2. Okay, so in example 2, we have a car that is purchased for $25,000. The value of the car depreciates each year. Each year the value is 4/5 of the value from the previous year. What we want to do is write an equation for the value of the car at any point in time t, where t is in years. Again, let's make a table. If we notice, again, let's look at time and say v for value of our car. Now, what we know is at time 0, the value of our car is $25,000. After 1 year, our car is only worth 4/5 of that amount. So what we're going to do is take $25,000 times 4/5 and get a value of $20,000. After 2 years, again, we're going to take that value, from the previous year, and we want 4/5 of that. So 4/5 of $20,000 is $16,000. And in year 3, we're going to take 4/5 of that value. And so we're going to take $25,000. Now we have 4/5 actually to the third power, if you look at our pattern that we have, and our car is going to be worth $12,800. Again, what I want you to notice is that when we look at these, we look at our table, we have our initial value of $25,000 in each case. We're going to take our 4/5, and then it's raised to the exponent, and the exponent is the number of years that have gone by. So if we were going to write ourselves an equation for the value of our car, the value of our car is going to be our initial amount, which is $25,000, times 4/5 to the t power, because that changes every 1 year. And then again, we could answer some questions. For example, if we wanted to sell our car after 5 years, what would be the value of our car after 5 years? So the value after 5 years would be V equal to 25,000 times 4/5 to the 5th power, which is equal to $8,192. We could also answer questions like, when will our car be worth half of its value, etc. But this lesson is focusing on how to write your exponential equations that match our applications. Okay, let's look at example 3. In example 3, we have a town that has a population of 15,000 people. Population is going to increase by 8% every 5 years. What we want to do is write an equation for the population at any time t. Now, again, I do want to start with the table to just show you. You won't have to start with the table each time, but I do recommend while you're learning to maybe write out a few values, give you a way to see the pattern and understand where the different numbers go. Now again, at time 0, we have 15,000 people. We are not going to know how many people we have again until 5 years goes by. After 5 years, we have an increase of 8% over that. So our table, instead of counting by ones like we did in the previous examples, we're going to have to count in terms of fives. So what we want to do is figure out how many people the town has at 5 years and maybe at 10 years. Now this problem is phrased differently than the previous example. It's not tripling, or we don't have a particular amount. What we do know is that the population is increasing by 8%. Now that does not mean we're going to take 15,000 and multiply by 8%, because all that will do is give us what the increase is. We need to keep our original people. So we need to keep our original 15,000 people. If we look, what we're really doing is 15,000 people plus 15,000 people times 0.08. Now if we look at that and you factor out a 15,000, then what we have is 15,000 times 1 plus 15,000 times 0.08. So what we have is really 15,000 times 1.08. Now the way to think about this 1.08 is this is actually the 100% of the people we started with plus an additional 8%, which is our increase, which will give us 108%, or 108% in decimal form is 1.08. So there's a couple of ways to think about that, but what we do need is to make sure you keep your original population, and we're adding to that population. So we've got our original population, which is represented by the 1, and then our increase of 8%, which is represented by the 0.08, or the 8/100ths. So if we want to know how many people we have after 5 years, we're going to take that 15,000 times 1.08. It'll give us 16,200 people. At 10 years, that's the next point we'll know, and in that case, we're going to do our 15,000 times 1.08, and remember, we're going to have done it once already, so we're going to do it a second time, and in that case, we'll have 17,496 people, and so on and so forth. Now, what we'd like to do is write the equation that goes along with this. So population at any time t is going to be, now again, think about what we're doing. We're going to start with our 15,000. So this number out front is our initial value. That's how many we're starting with in every single scenario that we've had. We are multiplying by 1.08. That is our increase in our population. And now, let's think about this. Normally, in the previous two examples, we just put a time up here of t. Is that going to work for this problem? If I look back over here, think about this problem is that when we had, in the second row of our column, we had just an exponent of 1. Well, our exponent of 1 corresponded to a time of 5, because it takes 5 years in order for our population to change by 8%. At 10 years, we only had an exponent of 2. If we look at that, then the way we get our exponent is to do what? We're taking the number of years that have passed by, and we're dividing by the time it takes in order for our population to increase, which in this case is 5 years. So if we look at that, after 5 years, our exponent will be a 1, and after 10 years, our exponent will be a 2. So our final equation for this is 15,000 times 1.08 raised to the t divided by 5 power. Okay, now that means, by the way, you can find out, we've been using whole numbers, but we could say, what is the population of our town after 3.5 years? So what if we wanted to know what the population of our town was after 3.5 years? Well, all we'll do is we're going to take our equation, we're going to plug in 3.5 for t, so we'll get 15,000 times 1.08 to the 3.5 divided by 5. Using my calculator, this gives me a value of 15,830 people to the nearest person, because we're not going to have parts of people that live in our town. So we are going to round to the nearest whole number. And so we're going to have 15,830 people in this town after 3.5 years. Okay, let's look at example 4. Okay, example 4. We have a very large ant mound with 70,000 ants. This is treated with an insecticide which will kill 20% of the ants every 4 hours. What we want to do is write an equation for the number of ants after t hours. Now, what we want to do is work this problem similar to the rest. I'm going to try to do this without making a table first. If you'd like to make a table, please do so. But let's look at the number of ants that we might have. Now, first of all, what we've realized from all of our previous examples is that what we are going to do is start with our initial amount. So the number of ants we have is 70,000 ants to start with. That's the number of ants we're going to start with. We need a factor that we're going to multiply by, and we know we're going to have an exponent. Now let's look at what that factor is we're going to multiply by. What this says is that the insecticide is going to kill 20% of the ants. We're actually not interested in how many ants are dead. What we're actually interested in how many ants are still around. So what happens is in this, our base number for our exponent is going to be the number of the percent of ants that are left, not the percent of ants that are dead. So what we're looking at is 100% of the ants that we started with minus 20% of our ants, which is 80% of the ants are actually left in the mound. Now 80% in decimal form is going to be 0.8. We know this happens every 4 hours. So like in example 3, what we need in our exponent is not just a t, but we're going to take t and divide it by the amount of time it takes for that change to occur, which in this case is 4 hours. So every 4 hours we're going to have 80% of our ants left, and we've started with 70,000 ants. And that's our equation. So we'll have 70,000 times 8/10 raised to the t divided by 4 power. And again, you could use that equation to find out how many ants there were at any particular time, or how long maybe it took for the ant mound to only have, say, 100 ants, and so on. So we can use that equation. Let's look at example 5. Okay, let's look at example 5. We have a clinic that reports 4 cases of the flu on a Monday. 7 days later, they have treated 18 cases of the flu. What we want to do is write an equation for the number of flu cases after t days. Now, I think we want to have a table in this case. Let's go ahead and look at what we know. We know that on basically day 0, that we have 4 cases of the flu. So we have 4 cases of the flu. I'll use C for cases. After 7 days, we know we have 18 cases of the flu. Now, notice that what we don't know is that multiplication factor. But what we're really interested in is 4 times what is going to give us that 18 right there. This is our number that we've been using as the base of our exponential function. So what I need to know is 4 times what number is 18? Well, if I put a question mark here and we look at that, solving for that question mark, that is going to be 18 divided by 4, and 18 divided by 4 is 4.5. So if we look at that, that's actually our factor. That's how many, that's our multiple of the number of cases that are increasing. So if we go to write our equation for cases, again, we want to start with the number of cases. The 4 is the number of cases we started with. Our multiplication factor is 4.5. That's how quickly our number of cases is changing. And how long did it take for that to happen? If we look over here, remember, if we read back up at our problem, it said it was 7 days later. So remember, our exponent then is going to be t, our time, divided by 7 days. Okay, and that would give us our equation for this particular application problem. 4 from the original number of cases, 4.5, which we get from the table looking at 18 divided by 4, what we need to multiply by to get from 4 to 18, and 7 in our exponent because it took 7 days in order for that change to occur. Okay, one more example. Okay, let's look at example 6. Popular Science magazine started publication in its current form in 1915. In 1990, the cost of the magazine was $1.95 an issue, and in 2010, the cost was $3.99 per issue. Assuming the cost is an exponential function, let's write an equation for the cost in terms of the number of years since 1915. 1915 would be our initial year where that magazine came out. So we're going to have to do a little more work on this one than we did on the previous ones because we don't know the initial cost of the magazine. We just know the cost of the magazine in certain years. Now let's look at then the how we are going to deal with this. We need to know, what we know is that in year 1990 that our cost of our magazine is $1.95. We know that in 2010 the cost of our magazine was $3.99. What we really are interested in, though, we don't want to use the actual year. What we want as our input in time, so let's go back in our table. So this is actually time since 1915. And so if we look at the time since 1915, 1990 is actually year 75, And 2010 is actually year 95 after the year 1915. So if we take 2010 minus 1915, we get that 95 years have gone by. So that magazine's been published for 95 years in 2010. And it's cost us $3.99. Now, what we want to do, again, is we're going to write ourselves an equation for cost. So I know what I need is some initial cost. Now, I'm going to write this initial cost as just a letter because I don't know what the initial cost is. So let's use I for initial cost. So this is our initial cost, and we're not sure what that might be. Next thing we know, though, is what we need the multiplication constant that goes in there. So what is our multiple for our exponential function? We're going to do the same thing to get that number that we did in example 5. So what we're looking at is the change between $1.95 and $3.99. What number would we multiply by here in order to get a change from $1.95 to $3.99? So what we do is we're going to take $3.99 divided by $1.95. That'll give us what we would need to multiply by. If I put that in my calculator, it is approximately 2.046. So that number that's going to go in here is 2.046. So our price is a little more than double over that time period. Now again, keep in mind that we're going to look at time, and our time in T in this case is the number of years since 1915, but how long did it take for that change to occur? It took from year 75 to year 95, or year 1990 to 2010. So if we look at the difference between 2010 and 1990, this took a total of 20 years for that price change to occur. So we're going to go up here, and in our exponent, we're going to need to divide that exponent by the 20 years it took for the change to occur. Now we're almost there, but notice that we're still missing a very key part to this. We still don't know what the initial price was, so we need to go ahead and find that. Now what I'm going to do in order to do that is to use one of the points that we have. So we can either use the first point or the second point in our table. I'm going to use the first one, and we know that in 1990 the cost was $1.95. If I take that information and put it into the equation that we have so far, then cost was $1.95. I do not know what the initial cost of that magazine was. This is 2.046 in our parentheses. Time, well, time, that's the number of years that have gone by since 1915, and that was 75 years, and divided by 20. So what I want to do then is solve for I. Okay, so I've got $1.95 equal to I times, okay, now I'm going to need to use my calculator a little bit here. Let's find 2.046 raised to the 75 divided by 20 power. That's approximately 14.652. To solve for I, we're going to divide both sides by that. That'll give us a final I value of approximately 0.13 if I'm talking about money. So that's 13 cents. So that says that we would have expected the price in 1915 to be approximately 13 cents. That gives us a final way to write our equation. So we're going to go ahead and take the equation we had above. We're going to plug in that value that we just found for I, which is 13 cents times 2.046 raised to the t divided by 20 power, and that should give us the cost of the magazine as long as t is in years after 1915. Now the one thing you need to keep in mind in this particular example is we did round several places. So I rounded originally to find our base and we rounded to find the initial amount. So if you want to be more precise, you want to leave more decimals. If you're not as worried, you could leave a few less decimals. But this should give us an approximate equation to find the cost of our magazine at any point in time after 1915, when the magazine was originally started. Hope this helps you write equations for applications involving exponentials. Thank you.